Hi friends, this is Pooja Kilaru. This is my final project in Advanced Operating System at Western Illinois University summer term, and I have another partner in this project. He's Harsha. The initial slides will be introduced by me. Coming to our topic name, it is Scalable, Eventually Consistent Counters over Unreliable Networks. This is one of the major topic trends going on in distributed system. That's why I have chosen this. Coming to the abstract of the topic that we have chosen, counters are an important abstraction in every distributed computing, where the use of counter variables in building up data types. In large scales, the use of counting events such as web page impressions, banner clicks, or social media network likes. The total topic will define eventually consistent distributed counters and presents an implementation of the concept, hands-off counter, scalable, and works over the unreliable network. All of these concepts will be gradually introduced to you. Here is the introduction. Even in a centralized settings, the increment operation on a counter is problematic under concurrency, right? Being one of the examples most used to illustrate the problem that arise if a load, add-ons, and store-on are atomic. In distributed settings, things are much worse due to the advance of shared memory, possibly unreliable communications such as memory loss, reordering, duplication, network partitions, or failures will be occurring. So, if one has a strongly consistent distributed database with the support of distributed transactions and counters can be trivially obtained. But unfortunately, such databases are not appropriate for large scale environments with wide area replication, high latency, such as possible partitions are not gone easier. So a navy counter obtained through get, add, on, put, and put transactions cannot be a scale performance wide given in many number of clients are there. So here comes the cap theorem, where the cap theorem says that one cannot have a consistent availability partition tolerance together. Here the cap in this cap means the C goes with consistency, A means availability, and P is partition tolerance. So what does it state that one must choose at most two of the three properties. Therefore, to have an always available services under possibility of partitions that in a worldwide scenario are bound to happen from time to time. Distributed data stores such as Dynamo, with no support for a strong consistency in distributed transactions and an API mostly based on one simple get and put operation obtaining a simple counter based on a problem. But sometimes that has been revealed a non-trivial problem involving many Hawk evolutions, and this approach is moving on to the next level, that is the CRD approach. In this CRD is this conflict-free replicated data types. In this, an approach towards obtaining provable, correct, eventual, consistent implementations of data types such as counters that are so-called CRDTs. That means conflict-free replicated data types. The idea is that each node keeps an CRDT replica that will be locally queried or operated upon, giving availability even under partitions but providing only eventual consistencies. Like queries can return stale values, but if like enough messages go through all the nodes will coverage to the correct value. These CRDT based data types can be built in trivial, triligant, unreliable communication. They are designed so that duplicates or non FIFO communications are not a problem. And this problem is an ease to explain, like this CRDT approach envisions a CRDT per participating an entity. In many of these, each entity needs have a unique identity, and they have to be keep mapping of participating entity IDs and some values of that. This set of keys, these maps will keep growing all the time. So more entities participation, the it will be preventing the scalability in that. So typically, a practical CRDT based approach to counters involving some server nodes and possibly some clients sorry, will exclude clients from the entities having CRDTs, having them server side only. But these will solve the scalability problem and allow the unreliable communication between the servers. And also the fault tolerance problem also it will be solving. This is because the basic problem with the counters is that the increment operation is not abundant, and therefore an increment request by a client will be done easily. And one more aspect is that like weight freedom and addresses to tolerant failure process, message loss or competent failures is not addressed in this. This means that the applicability of these mechanisms is mostly entitled with coupled with low latency failure free environment, such as multiprocessor serving a scalable alternative to look on a log based counter implementation will be done here. And now there is the another thing coming here is the classic distributed counters, which is another type. Here a counter is an abstract data type that provides a fetch and increment operations, which returns the counter value and increments it. The basic correctness criteria is usually a counter in a quiescent state, that is, when no operation is in progress. After n increments have been issued, will return all the values from 0 to n minus 1 with no value missing or returned twice. That is, when reaching a requisite state, all the operations so far have must have been behaved as if they have counted in some sequential order. This is what known as persistent consistency. And now coming here, even forgetting the strong variants that enforce linearizability, classic distributed counters provide this consistency that are strongly consistent if one of them is aiming for available and partition tolerance, that which are nothing more than installation of a cap theorem. And this is simply that formalizes the intuition that it is not possible to generate a globally unique numbers forming sequential in a distributed fashion cannot without communication between the nodes involved. Now this topic leads to the other one, which is eventually consistent distributed counters. We know that given the two strongly consistent nature of this classic distributed counters achieve availability and partition tolerance, a weak variant of a distributed counters need to be diverse. So this classic counters offer a two-in-one combination of two different features. Like the first one will be keep tracking of how many increments have been issued, and the second one will be like returning a global unique values. While undoubtedly powerful, the second feature is a problematic one of the aiming for an AP. So this splitting makes clear that one is not aiming for obtaining globally unique values. That means it fetch can return some value several times. and one can start thinking about possibly returning the steal value. Having two independent operations, one to mutate and the other to report, as opposed in a single automatic fetch. And we have three conditions here. A fetch cannot return a value greater than number of increment issued so far, and the other one is that at a given node a fetch should return at least one sum returned to the previous, that is 0 if such fetch was issued, plus the number of increments issued by the node between the two fetches. And the third condition is that all increments issued up to the given time will be reported eventually at a later time. It basically implies, namely, that if increments stop being issued, eventually fetch will report the correct counter value and the number of increments will be done, and these are reported along the updates. Coming to the system module, how these counters are being used in the way of memory are discussed in the system module. Now let us consider a distributed system with a node containing local memory with no shared memory between them. Any node can send messages to any other node. The network is asynchronous, there being no global clock, no bound on the time. It takes a message to the arrival nor bounds, and it is a replicative process speeds, and the network is unreliable. That message can be lost, duplicated, reordered. Some messages will, however, eventually get through. If a node sends indefinitely many messages to other node, so that means it will be delivered. It in particular, this means that there can be arbitrary long partitions, but these will eventually heal. So as we never require the data type operations block waiting for here, so we will be using a single action as opposed to the pair like op start for the input action, op end of r for returning a value of r. This allows to use op from t to I. That means the operation was performed by a node I at a time t. In this case, the fetch also for a result of that operation will be given, and there are some actions like fetch, increment for a data type operations, and send I of jm and receive of I of jm for message exchanges. Coming to the formal correctness criteria of ECDA, and eventually, consistent distributed counter is a distributed abstract data type where each node can perform operations like fetch, returning an integer, and increment, that is short for increment, such that the following conditions like hold, where it, where we are using this and this symbol, and these are some of the operations that we can do, like fetch bound increments, that is fetch of I this in this bounded with the help of increment function we are doing this, and the local monotonicity and eventual counting are done with the given formulas and with the functions that are available within us. um, Now coming to the eventual consistency. This eventual consistency means it guarantees that if no new updates are made to an object, eventually all access will return to the last updated value. So eventually counting is stronger than eventual consistency. It does not require increments to stop, and all CRDTs include a consistency criteria. And coming to the read on our rights, and it ensures that the effects of any rightness made within a session are visible to reads within that session. The analogous of this property is that substituting an increment of rights is implemented by a local monotonicity, coming to the monotonic reads, um, this using the formulation if a process has been particular value of an object and subsequent access will never return any previous values. So this property can also be obtained by local monotonicity. So now what's this naive CRDT based counters? So a state based CRDT, that what we have uh, learned in the previous slides. In this state based CRDT accounts to a replica that can be locally required updated. It directly provides availability and partition tolerance as all client visible data type operations are performed locally, and without no need of communication. Information is propagated asynchronously by sending the local state to other nodes. So what is that the merge operations amounts the performing of mathematical join the correspondent abstract states, deriving their least upper bound. Every data type operation is inflation, and that moves that the state to a larger value. So the CR in this CRDT concept can be used to trivially obtain ECDC. The local state will amount a version vector, a map node's IDs to non-negative integer, where a node wants to perform an increment, and this increment entry corresponds to the unique identifier. And also, it is easy to see that the version vector based counters respect the criteria for ECDC and fetch results by adding values that results for the increments are performed being um, bounded by the number of increments, and also the local increments performed are immediately accounted within the counter. Now coming to the other type of client problem is that the scalability problem in this client side. And the client side, there is a scalability problem in CRDTs where counters implemented are a version vector, all meeting all the criteria of ECDCs are unreliable networks, and the pure CRDT approaches assume that all the participating entities have CRDT. In this case, each participating node, that is both client and server sides, will introduce its ID on the map. Overall, it will grow the unreasonable sizes, making both the storage communication costs more. So the worst aspect is that the size does not depend only on currently participating clients. It keeps growing, accumulating all the IDs of the past clients and have already stopped participating also. And the other one is that the availability problem of the server side CRDs. Due to overscalable problem, current version vector-based counters do not use any pure CRDT approach, but uses CRDT server side only. This means that only a relative small number of nodes hold CRDTs, while clients uses remote invocations to ask server to perform an operation. And server-side CRDTs allow unreliable communication between the servers, including portions where the problem of unreliable communication between the client and server remains a kind of same. An attempt to circumvent this reliability problem through a general data agnostic communication layer bring back the scalability and availability problem. And coming to the hands-off counter, where this hands-off counter is one of the CRDT based counter mechanism where that meets the ECDC criteria and works in an unreliable network, and so opposed to simple versions of vector CD counters. It is scalable, and the mechanism allows arbitrary numbers of nodes to participate and adopts the CRDTs everywhere during the distinguishing clients, allowing an operation like fetch or increment to be issued by a node. Generally, it addresses the scalability issue by assigning trier number non-negative integers generally, and promoting a hierarchical structure, which is very much helpful, and where only a small number of nodes are classified as trier, where we'll be having 0 to n plus 1 triers, where n plus 1 will be the client to hands off to some of the trial like n will be in the server, making these entries corresponding to client IDs being garbage collected when hands off is complete. And here is an example where it this picture has three triers, and this represents a set of two data centers with a division them into the trier 0 as a top node and trier 1 as a middle node, and trier 3 will be the end, it will be the client, which is able to know the counters used locally, increments are handled, and take the work to increment the state eventually. And also this will be um, the the one server nodes per data center, and a very large number of trier 2 nodes are in each data center. The data store infrastructure would be made up of trier 0, 1 nodes, while a trier 2 nodes will be an end client nodes. Here comes the explanation for the network topology. Like it clearly explains the above picture to you now. The hands-off counter can be used in many different topologies. The simplest one is that um, it's a fully connected graph where any node can send message to any other node. In general, hands-off counter can work less with less connectivity, and there are some assumptions that make a network topology, like each link node should be bidirectional. And the other one is a network restricted to triad 0 nodes connected. Um, these assumptions allow the version vector discrimination in the triad 0, while also allowing a client U to start by exchanging messages with a server V and later switching to a server W if V becomes an unresponsive server. And any of these links can be down for some time, even possibly occurring in temporary network partitions. And next comes a distributor system. From here, my partner Harsha will be continuing.
Conflict-free replicated data types follows one complex algorithm. Here it contains two node elements. It is represented as node I and node j, and the replicas are called as Ci and Cj respectively. And the algorithm contains constants like I. It is represents for the global unique ID, and Ta represents for the node for it is a tier, and Ni is represented as their neighbors. Here Ci equal to init of I and Ti. Here init refers as a initializing the global ID and the tier node, and fetch of I is for the searching of an element. Here in the step 12 we can see that in the value I and j is merged into one pair, and in the step 13 it is says periodically, means it we have to repeat the increment of their each node of their increasing value. And step 14 comes from the elements of a node down to the neighbor value and sent it to the pair element. Here we can observe that Ca will remain unchanged, means the value will be holding the same value even though the j has incremented its value. And coming to the next slide, handoff counter data type. Here the server receives a counter value which is going to send to the client with the garbage collection, and the server take care of that. No duplication or no loss of message is being taken care of server. And we can see the steps with an example in the next slide with the node I and node j. Here the following steps is processed in this slide. A node I sends to ci and ci to j, and here j makes as each replica of cj, that is equal to merge of ci and cj. Here the operation merge operation creates an value of a data set, and in the second step j sends to c dash of j, and c dash of j transfers that data to another node I, and I data is transferred to c dash of I, and c dash of I has an merge operation of ci and cj. Here c dash j creates a slot and moves it locally, and in the third steps I is transferred to c dash of I, and j does transfer to another node c double dash j, and it has a merge slot for c dash j and c dash I. This merge matches with the first slot, the slot which was we created at the step 1, and it matches with the step 3. And in the step 4, the node j sends to c double dash j, and c double dash j sends to I node, and I sends to c double dash I. Here the merge operation, and having this second slot is transferred to the second step. It is moved to that node, and the token for that is removed, and the temporary items are sent to the garbage. And we can see that in this slide the mechanism should have three properties. Here only one slot is created and removed later, but the node received here is the duplicate message. And the second point is, if a slot is created, it does not match with others. And the third property comes is the duplicate message contains another slot. We can see that CRDT, it comes as a conflict free replicated data type. Contains the image contains of different clocks like logical clock, source clock, and destination clock. Here the destination clock is incremented when creating a slot, and the source clock checks and increases when creating a token. The middle tier of the node have the responsibility for the clocks for the transaction between a client and server representation. Okay, coming to the next slide, we can see the data type state. Here each value we have used in the diagram in this slide represents here it contains different logical clocks and different other values. The data types were used here as vals, where val comes for the maximum counter value that created with an increment of a value from one node to another is comes as val. And vals means it maps ids from ids to integer with a self entry if tier more than 0. And coming to SCK, DCK are these different types of logical clocks like source clock and destination clock. Coming to the slot, slot gives us a maps from source IDs of a logical clock, and the tokens are for the map. It maps from source IDs of logical clocks, and it's add an integer. Okay, now coming to hand of counter data type operations. The operations performed in the slide in the previous image. Here, the operation generally we performed was init, fetch, increment, and merge. Here, the init operation generates a new instance of a counter, where the fetch generates returns the highest counter value, and increments operation was it increments the value of the counter data, and merge is the value that it combines the total entities that have it received. And coming to the next slide, message exchanges. In this message exchanges, we can see that in this in this three-tier scenario we have taken the previous example. In a three-tier scenario, we can see that the tier 0 is the tier 0 consists of tier 0, 1, 2, and it is of explanation of two data centers, and tier 0 is the highest top value. See the top value contains, and it has the counter date type operation, and how it message exchanges are done was, as because tier 0 is the top end of the client, and tier 1 tier 2 are the serving nodes which has an end clients, and tier 0 comes as the top end, and tier 1 is the midway range, and the tier 2 is the end client. Here the messages can be accepted from tier 0 to tier 2. The messages can be passed to one node to another. Generally tier 0 is the lowest value, and it's uh, below consequences tier will be having the lowest values only. And we can see fault tolerance. Fault tolerance means when fault tolerance occurs means when a system is running an operation, and it has performed an operation and has when a failure occurs still, but the system did not stop, then this is called as a fault tolerance. In this fault tolerance, reliability of the system is long lasting storage of each node have local durability and fault tolerance. Here we have overcome the fault tolerance by receiving the request from the server by sending them in return to the messages. And coming to the next slide, how we are restricting the transmitted state through views. Okay, when we see in the previous example with explaining node I and node j of how they transfer the elements. When node I and node j element transfer the cache tokens from one having some of the greater tier client from their destination, means node I is having from a client tier 0, and node j is having a client 2 which has highest greater value, and node I represents as tier 0 as the source, and destination comes first for tier 2. Here the replica value of CA and CJ restrict the state such that due to the optimization between these tiers, due to this optimization, the small messages sent to each client are into smaller nodes. Due to this, we can restrict the state by viewing from one node to another. When coming to client retirement, here client retirement means it means client sending the result to an end client. Example like in the three tier scenario, tier 0 is sending its retirement statement to tier 2, and tier 2 nodes a token, and the token is kept in executed for the server to the client of a node and wants to retire. So that tier 2 will be having an idea of that tier 0 is going to retire of node. So it notes the token ID, and it starts executing from the middle range of the server, and the client will be retired. Now let's come to the next counter. Beyond counters. Beyond counters is the origin of the counters is made to 0. Here the values are changed its dimensions and by adding and taking the full value. This is done by generally this is done in beyond the counters, because the value accounted at each node is updated by a commutative and associative operation which inflates the value, means which increases a value from one node to another node. And for this we can see different types of examples like map of counters and PN counters. Here the map of counters explains about the IDs to integers by using operations like fetch and INCR and vals operations. When coming to the PN counter, this PN counter is going to explain regarding the same operations used by the map of counters. And coming to the discussion, till now we have done discussion with to achieve the reliability and availability. It uses in the distributed networks to achieve a replicated service, and the distributed transactions which fault tolerant commit protocol. And we have discussed the solution for many problems for like network failure and for the temporary and permanent nodes. And we can see that it is not necessary to retransmit messages with what has come an old version of the state as the current state. So it is sufficient to continue to transmit the current state to allow progress. And finally, conclusion. In the conclusion, we can see that the ECDT, which calls as ECDC, sorry, it's called as eventually consistent distributed counter. Here, the ECDC solution is called of hand of counters, which follows the CRDT theory, makes the protocol state. And the scalability solution has been solved in two ways. First, node ID enters are ID entities, node ID entries are not propagated into the system. So by this, it can be a solvable that scalable situation can be handled. And the second way of handling scalability is it allows a garbage collection of entries that participate in communication and retire. And finally, conclusion. Just we have completed the entire project. Since we can know that we can solve the scalability solutions, and we can also solve availability and reliability problems. And thank you.